Good morning, let's go. I've got 4 things I'm going to cover today. I'm going to have a final wash up on alpha and beta for type 1 and type 2 errors. I'm just going to give you a more visual example because we've been doing quite a lot of algebra on that. I'm going to give you a visual example of that. I'm going to cover something new. We're going to start looking at set theory, intersections and unions, that sort of thing, conditional probability, and Bayes' theorem, which is the highlight of today's lecture. So I'm just going to finish off what I was talking about yesterday in the tutorial about type 1 and type 2 errors. So we've got alpha, which equals the probability of a type 1 error, and beta equals the probability of a type 2 error, and the power of a test equals 1 minus beta. And of course you want alpha and beta to be small because they are errors and you don't want to commit errors, or you want to minimize them. You want those to be rare if you can. And you want the power to be large because it's 1 minus beta. Let me find a better color pen. And you'll remember that the final example, I didn't finish it because we ran out of time. But I was wondering what n I required, what n is needed to make 2 things happen. Alpha has got to be less than 0.05 and beta had got to be less than 0.2, and of course that means that the power has got to be greater than 0.8. And I just wanted to, the real reason I'm doing this is to point out that more data allows you to have a better test. It's better in the sense that although we are controlling the size of alpha, which we fix at 0.05, because that's the kind of thing that early 21st century scientists like to do, if we have more data, we can have a more powerful test, which is also good because it cuts down the probability of a type 2 error. Type 1 error, type 2 error. Type 1 error is rejecting the null hypothesis when it is true. So I can draw that. I can draw that quite nicely. The null hypothesis was that the probability of success was 0.5. And if we take the Gaussian approximation, this is the thing I didn't do because I used the exact probabilities with d binom. We're making a Gaussian approximation here. The mean is NP. And because it's the null hypothesis, it's n times a half, because that's the probability of success. The standard deviation is root npq, which in this case is the square root of n times a quarter, because it's a half times a half. So the standard deviation, put it here, root n times a quarter. And we define this little area here to make sure that that was the probability of alpha. If your observation was in this region here, we rejected it, and alpha equals 0.05 because we specified a 5% size of the test. Okay? Now we flick over to thinking about beta, which is the probability of a type 2 error, which you'll recall is failing to reject the null hypothesis, when it's wrong. So beta is the probability of being in this region here if the alternative hypothesis is true. And of course the alternative hypothesis, as it specifies in the question, is p equals 0.6. So if the alternative hypothesis is true, the number of successes looks like that. It's a different distribution. And in practice you won't know which one applies because you don't know if the null is true or the alternative is true. That's a very good question. The question was, how do you know if you're making a mistake? You don't. That's why randomness is hard to deal with. It's like any decision. You say, oh, well, if he thinks this and I do that, and you don't know. Until, in real life, you can normally find out.
What's the point of spending all this time trying to figure out this?
Because you're trying to minimize. Why are we doing this? We're trying to minimize alpha and beta and do something a bit, and try and have a small probability of committing an error, or at least be able to estimate it. I'm going to redraw that picture because I've drawn it somewhat infelicitously. Sorry. I'm just going to draw it over here. Sorry about that. This one is my null. This one in red is my alternative. And so here we can see this region here is beta. So we've got two types of, sorry. I'm sorry, it's the standard deviation. Let me write it out. The standard deviation is the square root of n p 1 minus p. Sometimes I write q for 1 minus p. But of course we've got two different standard deviations because the null is true, you bung p equals 0.5 into there, and if the alternative is true, it's 0.6. Yeah? So here we've got to, I'll go back to red. Here the mean is n times 0.6, not a half, 0.6 for the alternative world. And the standard deviation is the square root of n times 0.6 times 0.4, because it's 1 minus 0.6. Now, the question was, how do you know? Well, you don't. This is why it's hard to think, because you think, oh, well, if it's right, then I'm doing that, and if it's wrong. This is why we need this rather terse set of definitions to clarify our thinking about what kind of screw-ups is possible. What kind of screw-ups can happen? Well, that's one, and that's another one. And that's what they look like. Well, you've got to make some kind of a call on that. If you've only got a fixed amount of data, you cannot avoid one or other of those errors. We talked a few weeks ago about getting one alpha down to 0, but that bites you because beta, and beta down to 0 because then alpha becomes 1. There's a trade-off between these two things, but what I'm trying to do is to show you that more data gives a nicer, more equitable, not an equitable trade-off, but a smaller alpha and beta. Okay? And the question was, how many n do we need? How many observations? That was that topical steroid. I say that because I use steroids myself on my skin. We fix alpha as 0.5 and take our chances with beta, because that's the kind of thing that make people feel happy. Why people don't specify beta and take the chances with alpha is a social question, not a mathematical question. All right? So let's work out what this point here is, because we're going to fix alpha. Where is that point? Well, it's this. Let me just type and then I'll explain it. Oh, it's here. Q norm, 0.95. It's 0.95 because I want 95% of that. I'm not interested in that 5% here. I'm interested in the 95%. How far do I need to go on that black curve there to cover 95% of my area? Why 95? Because 5% is on the other side where I've screwed up with the type 1. Q norm, 0.95. Mean equals n times 0.5. Why is that? That's because that's the mean of my distribution. Where's the standard deviation from? That's the square root of n times p times, well, minus p is 0.5. This will fail because I haven't told it what the sample size is. So we'll have a guess. .58. So there's my test. If my observation exceeds 58, point whatever, 22 whatever, I will reject my null hypothesis. What's my size of the test? What's the probability of a type 1 error? 5%. Now I'm in a position to work out what beta is. Now I can calculate this red area here because it's the probability of failing to reject. That's if my observation is less than 58.227, which means I'm here leftwards. What's the probability of failing to reject that? Because this is a screw-up because you fail to reject it if it's false. There's a lot going on here. The only way to understand it is to sit down and think about it and talk it through and saying, well, if it's true, then that, and if it's false, then this. And what was the null again? Oh, the null was, you've just got to get familiar with it. It hurts your brain. I can't pretend it's easy. I'd love to recommend a Statistics Made Easy textbook for you. It's just a lie. It's hard. It hurts your brain. Even now, I wake up in the middle of the night and say, hey, 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 to my wife, hey, 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 listen, if the null hypothesis is false, then that means that we've not... And she'll say, what?
She doesn't care.
She says, shut up, Robin, you've just reinvented the Neyman-Pearson lemma. And I say, oh, yeah. All I'm saying is that even now it gets me, this. This is hard stuff, even now. And I have to go through this process. This is why I'm advocating memorizing the definition of p-value, because I say it to myself under my breath all the time. Anyway, let's work out what beta is. For n equals 100, that's our test. If the observation's greater than 58, we reject the null. So what's the probability of failing to reject it, getting less than 58, if it's false? Well, it's just this. Why 0.6? Because it's the alternative hypothesis.
Why not 0.6?
No, why 0.6, not 0.6? P-norm gives the area to the left, which is what we want. So the probability of a screw-up is now 35%. Screw-up, type 2 error. So beta is 35%. Too big, because the question specifies that beta must be less than 0.2. And it is not, it's bigger. Our probability of type 2 screw-up is too high. Are you with me? This is hard stuff. You watch the video and go through it. It's hard stuff. So what can we do? We haven't got enough power. Alpha's all right, because I've controlled that here. But beta, I said we'll control alpha and take our chances with beta. Sorry, tough, because beta's too big. I haven't got enough data. More data. Let's try n equals 200 and see what happens. What was the value that we came out with? It was 165 yesterday, wasn't it? 164, was it? Well, let's pretend we didn't know that. Well, let's try 200. No, let's try 180 and see what happens. All right? So first of all, I need to find this point here. I need to find that point there by finding how far we need to go before we get 5% error there. And that was here, wasn't it? Q norm. Now I've got a test which is reject the hypothesis if my observation exceeds 101. Yeah? So you see it's shifted because n's changed. Because n has changed, the mean has changed, and the standard deviation has changed. All that stayed the same is that area there, still 0.5. But the curve has moved because we've got a different n. So now we go back to here, and I've got to change everything now. Oh, no, I haven't got to change everything. I could combine all these into one super clever. Is that good enough? It is, because the probability of a screw-up is now only 14%. So we've got enough data to satisfy our requirements here. Alpha's still 0.05.
So it's satisfying both the 0.5 for alpha and less than 20.
Yeah, exactly.
For beta.
Exactly, because now it looks like this. It's narrower, in proportion at least. And now the alternative hypothesis, instead of having a massive overlap, it's got a much smaller overlap now. Yeah? So now we're in a position, you see how we've got more data so we can tease apart this very slight difference between 0.5 and 0.6. But we've got enough data to show a nice separation here. So there's my alpha, which is 0.5%. And there's my beta. But you can see how it's smaller because these peaks have moved further apart. They haven't moved further apart. They've got narrow. The distributions have got narrower because we've got more data. And it turns out that 180 is too big for our requirements because the power's too small. We're wasting observations here because if I only want a power of 80%, it's too powerful. Is that clear to everyone? This is hard work.
So you just adjust in downwards until you almost balance it out?
Yeah. Yeah, that's what we're doing. And of course, I could use some very clever numerical. I could combine that and that and that all in one line and give you some super slick answer. But this is conceptually what we're doing. Okay, I didn't have time to do that yesterday, so that's why I'm doing it now. Now on to something else. I'm really going to introduce Bayes' theorem, because Bayes' theorem and Bayesian analysis is another way of viewing probabilities. We've looked at type 1 errors and type 2 errors. We've looked at null hypotheses. Now I'm going to talk about a completely different school of statistical thought, a very controversial school, called the Bayesian form. But before I do that, I've got to cover a whole bunch of rather abstract seeming mathematical notation. So I'm just going to start with set theory. And this is not a mathematics course. If it was a mathematics course, it would be very different in flavour. But I'm going to start out with a nice little box, which I'm going to label E. It's kind of a curly E. It means everything. Then you say the universe of discourse. Okay, and I might have two sets in here. That one's A and that one's B. And A and B are subsets of everything. So a nice example might be you write it like this, equals 1, 2, 3, 4, 5, 6, like that, just 6 numbers. It could be anything. It could be people, it could be diseases, it could be planets. 1, 2, 3, 4, 5, and let's say 6. And they're like that. So the way you write it is that 2 is a member of A. Okay? So this is the A circle here, and it's got 2 and 3 and 6 inside that circle there. 3 is a member of A. This symbol here means is a member of. 6 is a member of A. We've also got 3 is a member of B, and 4 is a member of B. I'm not really going to define these mathematically because it'll take us too far afield. But you can see that there's all sorts of clever games I can play with this. This is called a Venn diagram. So if you want to work out regions that are common to both of those circles, you talk about the intersection. Sometimes I call this a cap. You've got a cup and a cap. Or intersect. It's just the intersection. It's this shaded region here. So if a member X is a member of A intersect B, then that tells me that X is a member of A, and separately X is a member of B. All right. Again, I'm not going to define that. I'm not going to pin that down perfectly mathematically because it would take us too long. It's obvious what it means. And we'll need this. We need to cover some theory first. And of course, there's another thing I can do as well. There's A, there's B. This shaded region here equals A union B. See, that looks like an N for intersection, and that looks like a U for union. Or the union of A and B. a very, very fruitful notation. So something's in the union, it's in either A or B, or both. I'll put some flesh on this soon, but we need some. We just need some notation first. Sometimes I write A and B over them, and sometimes I write them on the circles there. Shaded area equals a bar, not a complement of A. With a line over it. Sometimes you'll see it written like this, with this peculiar symbol, which I think appears on your keyboard somewhere. It's one of the symbols on the keyboard, I think. Or it certainly used to be. Maybe it's that one. No? Well, anyway, it used to appear on the keyboard symbols, but that's what computer people say. There's not A. So we can have jolly fun with this. You see, it's anything that's not in A. So B is irrelevant to this. See, the lines just go through B as if it isn't there. It's just anything that's not in A. So I can form things like A intersect B bar. Just bringing up these ideas together. And graphically, it looks like this. Yep. A intersect B bar. And if this was a mathematics course, I'd be going on and on and on about how the fact that A intersect B is B intersect A, and so forth.
So wouldn't it be, it's an intersect symbol, isn't it? So
That's right.
wouldn't it be in the middle rather than...
Yeah, but it's A intersect B bar.
So why
It can't have this one because that's not in B bar.
Yeah, so why have you done A? Because isn't that the intersect side of things?
A intersect B bar. So it's the intersection of these two sets here. There's A. B bar is that.
Ah, okay.
So the only bit that's in both of those is that bit there.
Okay.
Yeah.
Right, thank you.
And we can have jolly fun carrying on like this. I might want to shade off those two regions here. That's called the symmetric difference between A and B, which is by far the most interesting set operation on two sets. Because I want everything that's in A union B, but I want to exclude the middle. This is what you mean when you say when I say to the kids, you can either have an ice cream or a drink. Not both. If it was the union of an ice cream, they'd say, I want both. But when you say this or this in English, you say you can have the ice cream or the drink. You can't have both. So this is A or B, but not both.
So triangle.
Oh, I'm sorry, that's symmetric difference. Symmetric difference of A and B. Or sometimes you call it exclusive OR. Exclusive OR, because you say you can go to the beach or go to the park, but not both. And of course, my kids have got me wrapped around their little finger, so I've got to be very clear in terms of set theoretic notation when I'm offering them something. Okay, well that's great. I guess you've seen these before. How can we use this? Well, let's think of some more examples of how we can use set theory. I mean, I just gave you some numbers there. People. A equals male. So male people are inside here and female are out. So I'm in that circle because I'm left. Because I'm male. B equals left-handed. Okay. So here's me, and there might be other people dotted around here. This is somebody. Sure, I may as well write it in. That's male, and that's left-handed. So we've got this nice two-way classification of gender and handedness. Here's a male right-hander. That's my little boy, Zed. Here's a female left-hander. That'll be my wife, Leslie. And who's that? This is a female right-hander. That's my daughter, Alice. You can fill that as you like. So you might ask, what's the probability of being male? Well, we might say that's a half. That's nice. We also might say, what's the probability of being left-handed? That might equal 0.1, let's say. But you see, these two statements here don't really care about each other. They are those two statements there don't interfere with one another, because this one here doesn't make any reference to handedness, and this one makes no reference to gender. So they don't touch one another.